Thank you for having it. Thank you for having us today. I'm Russ Stenfort at Meta, and we have Chris Sabol at Google, and today we're going to talk about flexible data placement. So take it away, Chris.
Thanks, Russ. And I think we covered this. So we're going to talk a little bit about write amplification. For those of you that are not familiar, write amplification is basically when the host sends data to a drive, and there actually is more data written than what the host sends. So it's defined, the write amplification factor is just defined as the total data written to the media divided by the application data written. So for example, if we take an example with WAFF 2.5, the host, say, writes 1 megabyte, but there's 2.5 megabytes written to the media on the drive. In this case, it would be 1 megabyte of actual user host data and 1.5 megabytes of garbage collected data. And so, so you end up with this extra 1.5 megabytes of data that's both read and written as part of this WAFF 2.5 example. So why is this bad? Why is it undesirable? It basically results in a bunch of extra work the SSD has to do. So there's the media reads and writes that go along with the garbage collection, which can affect QoS and performance. There's additional wear for the additional writes, so the drive wears out faster. And the additional power. Writes are one of the more power-intensive parts of an SSD's operations, and so doing 2.5 times what you need to pushes you up against that power envelope much more quickly. For example, with random writes, if you have a write amplification of 1, your random writes would be the same performance, same throughput as sequential writes. Whereas with the write amplification of 5, your random write workload is running at 20% the throughput of a sequential write workload. So what does this mean? This is sort of kind of a real-world example from a Google data center. So if you have 28% OP in a drive and you're doing 4K random writes, and there's a greedy garbage collection algorithm in the SSD, you'd expect a write amplification of about 2.5. If you can drop that in half to a WAFF of 1.25, that has tangible kind of real-world benefits. If you were okay with the original WAFF 2.5, you can reduce OP in the drive, get extra bytes, deploy less drives, save on CapEx. If you were limited by the controller throughput or by power before, so you couldn't go to a larger drive, now with reduced WAFF, you can deploy a larger drive, which saves on CapEx and OpEx. You could, if you were wearing a drive out previously, now you may shift to the other side of that equation, not wear the drive out, not require kind of a mid-lifetime replacement, which can save quite a bit. And there's a performance benefit, right? Up to 2x performance on the write rate in this case. So in a world of kind of the other way of looking at this is in a world where all write workloads had a WAFF of 1.0, what would that mean? So you could get the OP in the drives would go away, right? Or at least drop substantially from the 28% example previously, giving you extra bytes per drive. The performance, the random and sequential writes would have similar performance. There's this property on drives where, until they're filled the first time, you get good random write performance, and then once it fills and you start getting into the steady state garbage collection mode, the performance drops off. That effect goes away. There's no need to precondition drives. The QoS improves for reads and writes, and media wear is reduced. Drives last longer. And power is reduced too. So here's a little history of the industry and write amplification. So back in the early 90s, the first NAND-based SSDs were introduced, and they required garbage collection, as we know. And the only tool that could be utilized to change the write amplification factor was increasing the OP or decreasing the over-provisioning to tune that write amplification. Fast forward to 2007, 2008, and the introduction of trim and deallocate functionality lets the application give hints or tell the drive that this data is no longer needed. So you can more effectively clean up and reduce write amplification. And now today we're talking here about flexible data placement, and we're working on it in standards. So it's coming soon. So last year I was here up here with Smarty talking about Smart FTL, which was Google's proposal for solving this problem. In the same room at a different time, or a slightly different room, Ross was talking about data placement, direct placement mode proposal from Meta. And over the last year, we've gotten together, we've aligned the two, kind of taken the best of both, went through the NVMe technical committee and been working on standardizing it. So to get a little bit more detail into kind of how we improve WAFF, we need to understand a little bit about the challenges of data center workloads and disaggregated storage. So in these data center disaggregated storage workloads, you have multiple applications running simultaneously, and the data is mixing on drives. So so in this example, you have 3 applications, all the data mixes together on the SSD, and you never really hit a stable, steady state garbage collection due to workloads coming and going and changing over time. You sort of increase OP till it gets to the point where it works well, or works okay, I guess I would say, and then you live with it. So with flexible data placement, we're going to give an example here. There's the same 3 applications are writing, and yellow is going to represent invalidated data. So without flexible data placement, the data comes in, it's written to an open superblock on the drive. They're written sequentially. So the timing of the data coming in from these 3 applications determines how the data is laid out in the superblocks. So you can see in this example, they get mixed together, and they're interspersed. So then when application A deallocates or deletes its files, deallocates its data, what you're left with are these holes in the superblocks, and those need to be cleaned up to make room eventually. And that results in garbage collection, and in this example, you end up with a WAFF of 3.0. So with FDP, it allows the host to tag writes with specifically which media units the data should be placed in. So in this example, it's with superblocks, and the 3 applications are essentially appending their data into separate superblocks, kept isolated. When application A deallocates its data, it frees up an entire superblock. There's no garbage collection needed other than the erase of the block, and the WAFF is 1.0. So next steps here, like I mentioned, we're currently traveling through the NVMe Express standardization process. I believe we're in a member review currently, hopefully exiting soon. Basically, bring your application use cases for discussion. We think this is a very valuable standard and technology. And we're looking forward to a world where getting to WAFF 1.0 on data center workloads is commonplace. Thanks.
So, a couple more comments. I should probably let you know where we're headed in the agenda today. We will have Mike come up and talk about the standard in that. And then we will have a panel with a bunch of people and take Q&A at that point in time. And so with that, how about we continue on with our agenda here?